Good afternoon and welcome to the Donald Julius Groen lecture, organized by the Institution of Mechanical Engineers Tribology Group. My name is Ardian Marina, and as the current chair of the IMechE Tribology Group, I have the great pleasure to chair this session today. For those of you familiar with the IMechE Tribology Group annual activities, you will know that traditionally the DJG lecture is also our award event where we have the medal ceremony and with the winners of the Tribology Trust silver and bronze medals, in addition to the lecture. This time, for obvious reasons, we are having to postpone the ceremonies to next year, but we would still like to use this opportunity to announce and congratulate the medal winners. So please allow me that in the next few minutes or so to announce the medal winners before we have Roger giving his DJG lecture. So without further delay, I will start with the Tribology Bronze Medal. The Tribology Bronze Medal is an encouragement award for engineers and scientists working in the fields of friction, lubrication, and wear, who haven't yet completed their formal education and training. It's my pleasure to announce that the 2020 Bronze Medal for Tribology has been awarded to Dr. Gary Nicholas. Gary's full citations can be found online, but briefly, Gary graduated from the University of Sheffield with a first-class IMechE degree in mechanical engineering in 2016. He subsequently went on to study for a PhD in tribology at the same university. His IMechE project involved conducting a detailed study of the lubrication of hydrodynamic thrust-bearing pads used in ultrasonic sensors. During his PhD project, Gary has been developing a method for measuring loads in rolling element bearings and inferring the lubrication conditions on each rolling element using ultrasound. These measurement techniques have been successfully implemented onto an operational high-speed shaft bearing of a wind turbine. Gary is already a hugely accomplished young tribologist who has published the results of his studies in both peer-reviewed journals and at international conferences, making him an extremely worthy recipient of the 2020 Tribology Bronze Medal. Congratulations to Gary for this well-deserved award, and we look forward to hearing about his future achievements. Moving on to the next award, the Tribology Trust Silver Medal Award is a national award in recognition of an exceptionally meritorious contribution to the science and technology of tribology. It's my pleasure to announce that the 2020 Silver Medal for Tribology has been awarded to Dr. Robert Ian Taylor. Again, Ian's full citation, which is quite longer than what I will read now, can be found online, but briefly, Ian gained his degree in physics from Cambridge University in 1984 and the PhD in applied physics and electronics from Durham University in 1987. In 1991, he joined Shell Research Limited as a researcher, where he initially worked on developing models to predict the overfilm thickness and friction of piston rings. He then developed similar models for journal bearings and valve chain systems. The analytical models and the associated software tools that Ian and his team have made a valuable contribution to improved efficiency in both passenger vehicle engines and the more specialized area of Formula One development. From 2006 to 2012, Ian was the technology manager for Shell's lubrication science team, and from 2012 to 2020, he was the technology manager in Shell's lubricants discovery hub. Ian retired from Shell in late 2020 and was recently appointed to an honorary visiting professorship at the University of Central Lancashire. Ian has published extensively in the field of lubrication science and tribology, has five patents, and is well known in the industry. He has received awards from the Society of Automotive Engineers and the IMechE. He is regularly invited to international conferences as both presenter and the chair session. He is therefore awarded winner of this year's Tribology Silver Medal. Congratulations to Ian for this well-deserved award. Now moving to the main event for this session, because it's last but definitely not least, the Donald Julius Groen Lecture Prize. The DJG Prize is awarded by the IMechE Tribology Group as a recognition of outstanding achievements in the field of tribology. This year, I have the pleasure to announce that the DJG Lecture Prize has been awarded to Professor Roger Lewis from the University of Sheffield. Roger is currently Professor of Mechanical Engineering at the University of Sheffield. He's also currently a Royal Academy of Engineering Rail Safety Standards Board Research Chair in WheelRail Interface Low Adhesion Management. Roger has had over 20 years experience of working on a wide range of tribology issues, but now mainly focuses on WheelRail interface and human tribology research. His lecture today will be on the WheelRail interface, and it is titled Understanding and Controlling the Complex Tribology of an Open System. Now, before I hand over to Roger, at the end of the lecture, we will aim to have a few questions. We'll have Roger live in the line, and please use the Ask Question tab on the right of the screen to make your questions throughout the presentation. So in the end, you can cover as many as your question as possible. So over to you, Roger.
Thank you, Ardian. I was very pleased to be the recipient of the Donald Julius Groen Prize this year. Many years ago, as the Tribology Group Chair, I introduced quite a number of speakers, and I feel very humbled to join that list of eminent tribologists who've gone before me. Today I'll be talking about part of the work I've done on tribology, particularly focusing on the WheelRail interface, quite a complex system, as I'll explain as I go through my talk. You can see here a brief outline of what I'm going to cover in my talk today. First of all, I'll give you a brief introduction to how I joined the world of tribology. Then a little overview of the WheelRail contact, so you can see just how complex it is. And then I'm going to work through some case studies of areas that I've worked on in relation to this contact before I sum up at the end. So this is where I joined the world of tribology when I got a letter through the internal mail from my soon-to-be PhD supervisor, Rob Dwyer-Joyce, offering PhD students in this rather unknown subject to me, tribology. We had no undergraduate module in tribology at that time at Sheffield, and Rob had only just joined the department. I'm glad to see that he thought I was a high caliber student, as he mentions in his letter. Anyway, off the back of that, I spent 3 years looking at these. So that's an engine valve and seat insert. So I worked for Ford trying to understand the wear mechanisms of these components within a diesel engine. And after that time, I got one of these, the much sought after pie hurling diploma from the Red Deer. So those of you who know Sheffield well will know that that's the closest pub to the department, and it's where you always went after your PhD viva to celebrate. Sadly, they no longer offer these badges or the accompanying certificate. So a little bit of Sheffield history there. So that was my introduction to the world of tribology. Where did I go then? Well, after doing a couple of postdocs with Rob, I joined the Department of Mechanical Engineering, initially as a teaching fellow, and then as a lecturer working in tribology. And you can see here some of the different areas of tribology that I now work in. As we all know, tribology is a diverse subject. tribology is everywhere, which is great. It means we can work on all sorts of things. So my work was kind of split between railway tribology and human tribology. But I've done lots of other things, as you can see at the bottom. So if you want to know more about what I've done with whiskey bottles and apples and more laterally sandwiches, you'll have to ask me at another time. But the main focus of the talk today is on the WheelRail interface. You can see a nice photo of a contact there, which shows some of the things that can happen in and around the contact. As I said earlier, it's a very complex system. I think possibly the most complex tribological interface. This is largely because it's in an open environment, so obviously it can be affected by many external factors. Obviously the environment itself. Lots of different products are applied to the interface as well to try and control the conditions within it. But as a train passes down the track, the contact conditions are constantly varying. So the forces, the level of slip within the contact, they vary all the time. So this makes it a very difficult contact to understand and also to replicate within a test environment and in a modeling sense as well. However, it's very important to understand the contact, obviously to be able to produce complex models, for example, multi-body dynamic simulations. You need to understand the contact conditions. The contact conditions drive the damage mechanisms, create the friction conditions within the contact. So we need to understand them, and that will help us to design better trains, better brake systems, to develop different products to actually control the conditions within the contact. This is all very important because more and more people want to use trains. And so in order to make more trains available, we need to push towards this 24/7 railway system. But in order to do that, obviously, we have to reduce the need for maintenance and keep the train performance really high. And obviously, the WheelRail interface is behind all of this. It's probably the most critical interface in the railway system. So the work I've done in all areas of tribology that I've worked in has very much focused on at the very low technology readiness level end, understanding the fundamentals. Obviously, in a tribological sense, that will be to do with friction, wear, rolling contact fatigue, and other mechanisms that are happening within the machine element interface. And then using this fundamental information to develop tools that engineers in industry can use. That's always been really key for me as an academic, wanting to make my work have some impact. Obviously, it means as well that you can get out in the field and do some proper hands-on engineering as well, which is always very good. So that's been a really big focus of mine. And recently, I've been lucky enough to be able to do quite a lot of that, as you'll see as I go through my talk. So where do we start when we're trying to understand an interface? Well, the most important thing is to understand exactly what's going on in the interface. And as all tribologists know, it's actually very difficult in real time to measure what's going on inside a contact. I mean, it is very important that we do this because we need to know how friction and wear mechanisms actually evolve as an interface is happening, if you like. So you've got one element rolling against another or sliding against another. What's happening? We can look afterwards, obviously, to look at surfaces to see what's happened, but actually we need to know what's going on in the interface in real time. At Sheffield, mainly through Rob Dwyer-Joyce's work, we've been developing ultrasonic measurement techniques for looking at machine element contacts, amongst other things. And we used this many years ago to start looking at the WheelRail interface. So we're able to scan an ultrasonic transducer over an interface. And where you have a rough surface contact, you have little pockets of air trapped. Ultrasound reflects at an air interface. So you can look at the ratio of the reflected voltage that you're pulsing up at the surface and a reference voltage, which you take where you have the bottom part of the interface taken away. And this gives you a reflection coefficient, and this reflection coefficient can be related to the contact pressure in a contact via the interfacial stiffness using the equation shown on this slide. So when you're measuring an actual interface, you can scan, get your map of reflection coefficients, and through a calibration taken separately, you can produce a contact pressure map, which is really useful. In the first instance, we did some very simple scans of a static WheelRail interface using a focusing transducer. You can see the results here. Should note that this is not a run-in WheelRail surface. This is quite a new wheel against a new rail. So it's not a nice smooth surface on the components, which is why it looks quite fragmented. If you compare to Hertz, you get quite good correlation. Obviously, the real contact's slightly bigger because of that roughness. And the peak contact pressures are much higher because of that roughness as well. And this information on its own is very useful to start validating models of interfaces. But of course, the actual contact moves. So there's only so much we can learn from doing static scans. Our next step in this work was to use some ultrasonic arrays. So these are similar to things used in medical imaging, so when you're looking at babies in the womb. What this allowed us to do was to insert the array into the rail so that we could get a snapshot of the contact within our full-scale WheelRail rig. Within this rig, we're loading an actual train wheel against the length of rail, as you can see in the picture there. The rail's then pulled underneath the wheel, and we can apply different levels of slip and realistic normal loading conditions. Now, obviously, we're taking these contact scans at a much higher speed, so we lose a little bit in terms of resolution, but you can see here we're capturing a nice image of the contact, which we've now validated through some finite element analysis, as you can see in the image in the bottom left-hand corner. Of course, this step is great, but not many people are going to allow us to cut a hole in the rail for us to insert an array. So we needed to find a slightly different way to take this measurement technique into the field. So we've done some work developing more flexible arrays. These now can go underneath the rail heads. So we're using a slightly different approach here. We're going pitch catch. So one transducer is sending out the ultrasonic signal, and then another is receiving it to the other side of the rail. Again, we lose a little bit of resolution here, but we've now got a valid technique we can go into the field with to do actual measurements on track, as the transducers won't in any way interfere with the passage of wheels over the train. So we're working towards that at the moment and finding an opportunity to do some measurements. In the meantime, we've started to apply the ultrasonic technique to a slightly different track-related problem. Longitudinal stress in the rails causes problems. You can see here an example of where some problems have arisen during the summer when the track gets hot and has buckled. So this is why you quite often get speed restrictions in hot weather to try and avoid this happening. So we've developed a technique by which we can actually monitor the stress in the rail. You can see some of the transducers here being tested in the lab. And actually this week we've had people out on track in Stoke doing some measurements on some actual rail. We were lucky enough to get an opportunity to tag along some testing of a system that's used to alter the stress in a rail using an induction heating technique. So that's been really exciting for us. hopefully soon we'll be able to use this to monitor track on a more long-term basis. So once we can understand what's going on in the interface, it gives us a better set of tools to understand some of the other aspects of WheelRail tribology. The first thing I worked on after finishing my work on engine valves was wheel wear modelling. And that was based around developing tools based on multi-body dynamic simulations to predict how the profile of a railway wheel evolves as it's passing along the track. This schematic shows, in simple terms, how the kind of overall model works. You've got your vehicle emission information going into the multi-body dynamic simulation. You get some global contact conditions. You then run this through a local contact model. This breaks the contact down into a mesh, and you get forces and slips within each cell within the mesh. And then we can use this information alongside a model of material removal at those conditions to predict how the profile evolves. Obviously, my main role within this work was to define those rates of material loss for the different contact conditions. We used an approach that's well established within the railway industry now, the T-gamma approach, relating wear to the amount of energy within the contact. So I did a lot of work looking at the different regimes of wear, from the very mild conditions you may get in the rail head wheel tread contact right through to the very severe wear you may get in very sharp curves in the flange gauge corner contact. And you can see here how subsurface the features within the wheel material change from a very thin layer of oxide, very low levels of deformation, through to the very severe end where you've got lots of material flaking away and quite high levels of deformation. So these wear coefficients you see defined there are the things that can be used alongside that mesh of contact conditions within the WheelRail interface to predict how much material is removed and then assess how the profile evolves. Obviously, these tests were carried out in dry conditions. In order to validate, we were lucky enough to have access to some data from the Lucchini full-scale roller rig, quite an impressive test rig, as you can see, that allows you to mount a whole axle within a rig and load it and undergo an actual train mission. Again, though, this is in a lab, so it's dry conditions. Actually, that was convenient in this case because we had a dry prediction and dry validation case. We could do a really good comparison, and you can see here that the prediction matches very well what was measured in the rig. So that's great. However, when you start looking at train operation in the field, you're getting a very different set of conditions. It's very rarely going to be dry as such. There's going to be rain, dampness, leads on the line, applied products. So how do we deal with those? And this really is where we start getting into the limitations of this kind of approach. We need to have a much better tribological understanding of what's going on in the interface. At the moment, the way the different interface conditions would be dealt with would be to change the friction coefficient, which for multi-body dynamic simulations, as we're looking at here, would actually be an input. Well, of course, this is all the wrong way around. Friction results from the conditions you have in the interface. It's not an input. However, if you think, for example, you're going to be going around a curve where there's some grease lubrication, then you could reduce the friction coefficient. Or if it was going to be wet, then you could reduce the friction coefficient. Well, within the modelling approach, as we've prescribed it, that would take you back down to a lower T-gamma value, but down this dry wear curve. And as you can see from the graph on the left, it would obviously give you a lower wear rate. But if, for example, you had a wet condition, actually you need to be jumping on to that much lower wear rate curve at the bottom of the graph. So immediately you are getting some inaccuracies creeping in. And of course, going back to friction being an input, if you're estimating the friction coefficient and you haven't got it quite right, that initially can give you some errors, because then your simulation will be calculating the wrong forces in the contact. So we needed a much better understanding of how friction and wear vary with different third body layers to improve our approach to modelling. As you can see from the graph on the right-hand side, we started on that process. We're gathering more data on how the wear rate varies with different T-gamma conditions for different third body layers, which can now be fed into improve wear predictions. This is a long process, obviously. There are other issues with the whole idea of using T-gamma. That is an amount of energy. Not all that energy will be dissipated in removing material from the wheel and rail. Some of the energy will be lost as heat, vibration, noise, and how do we actually sort of work out exactly how much is going into wearing and damaging the materials. In fact, what we probably need to do is look at a whole different approach to estimating how the materials are worn. I've now had a research collaboration with Virtual Vehicle Research over a number of years, where we've looked at a number of different issues within the WheelRail interface. We've recently started a couple of projects collaborating on looking at different ways of predicting wear. One more statistically based, so using field data. When I started this kind of work, it was very, very difficult to get hold of data from the field. Now, way more measurements are being taken, so actually you can start to use that data in a statistical way to predict what may happen in terms of wheel wear. And within this work, we'll look at different traffic mixes as well, so you can see what happens when you have different trains going down the same line. So that's quite an exciting development. And then, of course, there's more physically based models. So we have some work going on discrete element modeling of the wheel materials. You can see here how we're trying to develop simulation of how the deformed layer at the surface of a wheel or rail develops over time using that discrete element modeling approach. And we'll obviously be working alongside that to generate experimental data to validate these models. So really interesting developments. Of course, at the same time, we have to start looking at how, as tribologists, we can actually reduce wear. It's not a good thing that wheels and rails wear out. It costs lots of money to replace them. When you look at the cost of replacing track, is very, very expensive. Ironically, the only very tiny part of that is the cost of replacing the rail. I think it's been estimated at about 8%. Most of the money's lost in terms of closing the line down, getting all the equipment in needed to actually replace the rail. And one area we looked at Sheffield now for a number of years for reducing wear of rail is laser cladding. So this is where you're applying a layer of premium material to the rail that's very hard and durable. And it's applied by focusing a laser onto the rail material and then feeding in the premium material as powder around the laser beam. So you have this little melt pool mixture of the rail material and then the premium material feeding in. And that gives you a very well bonded layer on the outside of the rail. I say that gives you a well bonded layer. You have to work hard to understand the cladding parameters you need to achieve that good bond and to make sure the heat affected zone isn't becoming embrittled with too much martensite. So it does take some time to get those parameters right. As you can see from the pictures, we've looked closely at what happens when you have a good clad, but also what happens when you have a bad clad. Obviously, the railway industry, very safety critical. We need to understand what might happen if a poor clad layer happened to be imposed. The way we're looking at using this is that we would apply this to quite high value track components. Most of those would typically be removed for refurbishment, but the idea of in situ repair is interesting. So we've looked at some repair scenarios. Here you might be more interested in actually applying the same material as is already on the rail. So if it's R260, we might want to clad R260 in to make a repair. We need to understand that though, because the properties of the clad repair won't be exactly the same as the bulk rail because of the thermal processing that it's gone through. In the graphs on the right hand side, you can see roughly where standard grade rail fits in the wear graph at the top. There were some clad layers that gave a worse performance, but there were some that gave a very much better performance under the conditions we tested at. And it's those materials we've gone forward with in our subsequent research. The graph with the blue bars, that's showing the rolling distance required to create some rolling contact fatigue type damage. Now, in fact, most of the materials ran out, so in that sense, we didn't actually create any cracks in them. They're very hard to deform. You need that kind of deformation process started to initiate and grow cracks. So a lot of these clad materials are promising in terms of reducing wear and rolling contact fatigue. Of course, this has been done on twin disc testing, so a very simplified contact. We needed to look at how it fared in a full-scale scenario to build confidence and to get permission ultimately to get it out into track. So we clad some rail and we ran some wear tests. We were getting very much lower wear rates with the cladding, which reflected the scaled twin disc testing results. We also looked at insulated block joints. So these are the joints that separate sections of track electrically for signalling purposes. So it's very, very important that these sections of track remain isolated. As wheels run over the polymer slices that are inserted between the ends of the rail, obviously the rail material flows and there is a chance that it may bridge a gap. If a track circuit shunts, it can be very, very costly. The repairs are very simple to do. You go out with a little Dremel and you cut the material away and it's okay. But by losing that bit of line for a time, a lot of delay minutes accrue. So we looked at the idea of putting a laser clad material either side of the joint to reduce the amount of flow that occurs. And we managed to simulate that in our full-scale WheelRail rig. And we managed to keep that gap under control with the laser clad material. For situations where with a standard grade material we would have shunted the track circuit. So to build on this, we're now at the point where we're having some insulated block joints made up to insert into track at the British Steel plant in Scunthorpe, which is a very exciting development for us. So a big area I've worked on since starting work on the WheelRail interface has been management of the friction within the contact. This is important for quite a number of reasons. Obviously, controlling the friction helps to a certain extent to control the damage within the interface. So you would want a low friction solution in the flange gauge corner contact as you go around a curve. At the same time, you want to reduce the friction to reduce energy consumption, so the amount of fuel your train's using. And when you have low friction, you might want to increase it to improve your braking and traction. So that's all encapsulated in this graph, which shows the different levels of friction and how you might use friction management products to control those. We've worked on all of these different types of friction management products and also focused a lot on how we might develop benchmark tests to assess the products. It's very important you can understand the performance of a product before it's approved to go in use on the railway network, because you want to eliminate all risk surrounding the product and know that it's going to do the job you want it to do. We traditionally used the same kinds of tests as many other people related to twin disc testing or tests that mean you end up cycling over the same bit of contact again and again. This actually makes assessing the performance of products very challenging. So more recently, we've started working again with virtual vehicle research on a slightly different test approach. It is one that's been used before for this kind of work, but a very long time ago. So it's high pressure torsion testing. Here we're bringing two flat surface specimens together under a representative contact pressure. We're loading them together and then twisting under controlled rate of speed. This means, as you can see in the graph on the bottom left-hand side, we get a certain elastic regime, and then beyond a certain point, we get gross sliding. And we're essentially measuring the shear stress in the contact. Here is plotted against mean rotational distance. This has many advantages. It's a one-cycle test. It means we're not cycling over the same point on the materials a lot. Makes it much easier to apply third body layers and to control roughness, which is very important in assessing friction levels. The data we obtain from the testing can be used with rolling contact models, for example, the enhanced creep force model that has been developed by Virtual Vehicle, but there are others. And we can use the data then to create a creep curve, which is a very important bit of information for assessing what's going on within the contact and how third body layers and applied friction management products perform. Just wanted to show a little case study of how the HPT data can be used alongside something like the extended creep force model to enable us to do full-scale predictions. So on the left-hand side here, you can see some measurements we took with a top-of-rail product. So this would be applied from either an onboard system or a wayside system onto the top of rail to be picked up by the wheel if it's wayside and carried down the track. These are primarily applied to give you a kind of medium level of friction. Remember back to that earlier plot. That has benefits in terms of energy saving, but also in terms of wear and rolling contact fatigue reduction, noise reduction, and so on. We did lots of tests with lots of different amounts of product. You can see one particular amount here. And the data is showing what happens as you progressively cycle over and do different numbers of cycles over the product. The black line at the top obviously being the dry value. So here you can see we're getting a friction coefficient somewhere between 0.2 and 0.35, which is very typical of a good top of rail product. This data collected from the HPT testing was used to tune the ECF model and create a parameter set we can use to then carry out predictions for other types of contact. And that's what we did. So we're very lucky to be able to obtain some locomotive data. So this is a locomotive running over track where the same top of rail product had been applied directly to the rail head. So the graph at the top shows the predictions from our newly tuned extended creep force model. So you can see traction coefficient against creepage, and then the same measurements at the bottom from the locomotive. You can see there's quite a difference between the nominally dry values. Well, obviously our dry values in our prediction are for dry values. Within the field, it was actually very difficult within this testing environment to achieve dry. So it's very likely that these were actually wet in reality. More importantly, though, if you compare the data for the top of rail product, you can see that there's really good correlation between the predictions and the actual measurements from the locomotive. So we're very clearly showing you can do some lab tests, tune a model that is then able to be used to give valid predictions of what will happen in the full-scale contact. It's really, really useful. So one way we can use to maintain good interface conditions for the wheel and rail, and one that's practiced worldwide, is rail grinding. So that's used to maintain the profile of the rail in its optimum condition. That gives contact conditions that should reduce damage and give better ride comfort for passengers in trains. But it's also used for removing damage that's accrued as well. So there may be cracks or dealing with high levels of plastic flow in rail or wear. We've been working on rail grinding for quite a long time now with Network Rail. That's been mainly focused at developing new grinding techniques. But we also have a collaboration with the National University in Colombia, where we're working at understanding conventional grinding a bit better and how this leads to white etching layer formation in rail in the high temperature pressure conditions that exist in the grinding stone contact. It's important to understand this because the white etching layer can lead to other forms of damaging accruing after grinding when the trains start to run over the track again. They can be crack initiation points, for example. You can see here the rig that the Colombians have built to allow grinding of our twin disc specimens, which means we can grind a sample, we can analyze it, but also we can take it away and carry out rolling sliding tests on it to see what impact the grinding has on subsequent damage formation. You can see the rig starting to run here. So grinding stone spinning at 90 degrees to the disc, so we can actually grind the disc. And this can be carried out at different forces, speeds, and so on. Afterwards, we can section and look very carefully to see what levels of white etching layer have formed. Here you can see some analysis on different rail grades. We get very different forms and levels of white etching layer under the same grinding conditions and different rail grades. Very important to try and understand this as more premium grade rails are being used at the moment. We need to understand how they can be ground in the most effective way. As I mentioned, we're trialing some new grinding techniques with Network Rail. Initially, this was driven around the need to try and improve the speed of the grinding process, which at the moment is relatively slow, maybe running at sort of maximum of 10 miles an hour. So using super abrasives that are used extensively in the railway industry, we should be able to speed up that process. But actually, more importantly, as we've been looking at more recently, it should be able to give a much better surface quality to the rail in terms of both roughness, but also that phase transformation. So we should get very little or no white etching layer using this approach. So we've just developed a new rig, which we're in the process of commissioning, similar to the one in the top right-hand corner there that we have already, that will allow us to really explore the potential of this technique. And we're working on another project where we're developing a demonstrator that hopefully one day will be able to fit into an actual grinding train to grind track. Obviously, putting roughness onto the rail changes the contact conditions quite considerably. You know, in terms of grinding, we're going up to roughnesses of maybe 10 microns, which tribologically is very, very rough. So we need to look at how the contact may evolve post-grinding. It's been noted in the past that wheel climb derailments can occur shortly after wheels have been turned or rails have been ground. So it's obviously potentially creating a very high friction contact conditions under some circumstances that can lead to a problem. Again, we've gone back to our HPT testing now and combined that with our ultrasonic measurements to look at how the contact conditions vary when you have a rough surface. So we could look at the contact stiffness and see how that links potentially to friction, but also the real area of contact as well. So that's some very interesting ongoing work we have at the moment. I've been very lucky in the last couple of years to be working on a Royal Academy of Engineering Research Chair position, which is supported by the Rail Safety and Standards Board. This is built all around understanding and managing low adhesion in the WheelRail interface, which is a problem we're all very familiar with. It hits during autumn, so we've just come through the really bad period for this year. There are a number of streams of work within this program. from our point of view, mainly based around fundamental understanding of the problem and the types of mitigation that are used, but we're also working on a number of other areas like forecasting of adhesion and rail cleaning, for example. The consequences of low adhesion, well, I think we all know what they are in terms of safety issues with trains slipping on the track, perhaps passing signals of danger, or running through stations. There's a big cost in dealing with this as well in terms of cleaning the rail and managing the wheel-rail interface conditions during autumn. So, for example, you may have seen the railhead treatment trains running through with the blue wagons blasting water at the railhead. So this kind of big operation kicks in every autumn to try and make sure the trains are performing better given the low adhesion conditions. I'll give you a few snapshots of some of the stuff we've been working on recently. So first of all, looking at the low adhesion mechanisms. Some very recent work that's just been published in the Proceedings of the Royal Society on tannins within leaves and the effects they have on leaf friction. You can see here, again, within our twin disc machine, we've run wet, as you can see in the blue bar, then with a kind of leaf tea mixture, obviously with tannins in, gives you very, very low friction. So here we're kind of below 0.05, which is getting to the ultra low region, as would be defined for the wheel-rail interface. And then when we test with that same leaf tea mixture with the tannins removed, we get much higher levels of friction. So we're really starting to get to grips with the chemistry that's going on in the wheel-rail interface and understanding what those low friction mechanisms are. Obviously, understanding these will help people develop new mitigation methods that hopefully overcome those particular problems that we've identified. We've done a number of projects looking at modelling the effects of friction in the wheel-rail contact, initially looking at what we call wet rail, so it's mixtures of small amounts of water and oxide in the interface. And then more recently, we've extended that approach to look at leaves. So we did some extensive testing on the University of Huddersfield's nice full-scale rig to generate initially leaf layers. You can see them here being grown as we feed leaves into the interface under low speed. See here the leaf layers growing on the wheel in the bottom left-hand corner. Initially bright brown and crusty, and then they become that more familiar black colour after you've carried out some braking events. So we set up the rig to do braking. There's a tread brake bogey on the rig, so we had to jack up one side so we could brake there and then not brake on the other side where we're generating our leaf layers. So just to show you some typical output from the rig, so the top left-hand graph is in dry conditions. So here we're up at about 0.4 for friction levels. And then when we start to apply leaves in these lower graphs on the left-hand side, you can see friction is almost completely consistently below 0.02. And that was for whatever load we applied and for whatever speed we ran at. So remember, these are representative speeds and loads for train operation. So very, very low friction. This data was used to parameterize a model using the POLAC approach. You can see the graphical user interface through it here. So you can put in wheel-rail interface conditions, contamination type and amount, and then you can output a creep curve, as is shown in the middle graph. So this can be integrated with, for example, a multi-body dynamic simulation. So you can assess how train performance is affected by having those low adhesion conditions. The original model, the WheelRail model, was integrated into the train braking model, Labrador, which the University of Huddersfield had built. So look at braking situations in low adhesion conditions. It's hoped that this model, the LILAC model, will be similarly built into a braking model, so we can see how train braking is affected by low adhesion due to leaves. Again, this helps in terms of perhaps changing how braking operation works, or perhaps ultimately changing brake design to deal with this situation. Very recently as well, we've been developing new ways to forecast low adhesion. Here, again, with an RSSB project, we've been looking at neural networks that can use pictures of the railhead and the track surroundings and environmental data to predict friction. The graph at the bottom shows a comparison of predicted and actual values that we've measured. You can see here one of my students out on track. That was actually from November the 13th this year, so we're busy gathering more data for this. So this is quite an exciting development. You know, we can see perhaps one day a sensor pack being on the front of a train, capturing the images and data and giving a real-time prediction of friction for that bit of track that could be used, if not by the driver of that train, but perhaps the driver of the following train. Very exciting project we've worked on very recently as well is a new technology for railhead cleaning. I mentioned earlier that at the moment railhead treatment trains use water jetting, which is pretty good at removing contamination levels on the rail, but the trains are very big and there's a real gap in the market for a smaller, more flexible system to do this. And we've developed a technology based around cryogenic treatment, so firing dry ice pellets at the railhead to clean off leaf layers and oxide and water. So essentially we're firing very cold solid CO2 particles at the surface. Because they're cold, they embrittle the surface. They're coming out at supersonic speeds due to the nozzle design, so you've got a lot of kinetic energy there breaking up the brittle coating. And then the particles themselves, as they sublime and turn back into a gas, create these mini blasts. So you've got an increase of volume of about 800% during the sublimation process. So a number of mechanisms combine there to give really effective cleaning of the railhead. You can see here the system on the back of a small road-to-rail vehicle. This is a system we tested in the Supertram depot in Sheffield. You see the nozzles here pointing down towards the rail. Very wet day here, lots of oxide on the railhead as a result. You can see the blasts of dry ice pellets coming out now. And then as we move down the track, you can see that the railhead's being cleaned really effectively, a nice clean band of steel there. So we can run this kind of vehicle up to 10 miles an hour. That's the speed limit for these vehicles on track. But what this means is we have a really flexible solution that can be implemented in places the railhead treatment train can't reach. We got approval last autumn for trialling this in 5 different sites around the UK, different types of line. See here the Land Rover Defender pulling a trailer with the cleaning equipment on, and then some really nice clean railhead there post cleaning. So that was last autumn. This autumn we've been back out on the West Highland line all autumn cleaning with that system, but we've also been developing some new systems, which is really exciting. So one has been trialled over the last 3 weeks on the Nexus railhead treatment train. So Nexus is run the Tyne and Wear Metro. You can see their flatbed wagon with their water jetting system on. We've been able to build our cryogenic treatment system around that. And yeah, we've had some really nice results from that. That's obviously at much higher speed than we achieved in the road-to-rail vehicle. And then in perhaps a month or so, we're also going to be trialling a system built into a passenger train. So if we can effect cleaning more frequently using a passenger train, that could be really, really exciting and make a really big difference to the train operators in terms of cleaning lines that at the moment are very difficult to clean, particularly with a railhead treatment train, because that needs sort of track possession. At night, it can't run in between other trains, so it really restricts the amount of cleaning you might be able to do in the day when the contamination might start to build up. So some very exciting developments taking our technology out into the field. been quite stressful this autumn, but also very enjoyable. So, coming to the end of my talk now, you can see here in summary some of the areas we've looked at, and you've got a really good understanding now of how complex a WheelRail interface is, how much is going on tribologically within it. Our work has hopefully taken some of that fundamental understanding which we've gained in a variety of projects and developed it into tools now that the industry can use, and whether it be benchmark tests or models of friction or stress measurement techniques, or railhead cleaning technologies. And hopefully one day this new approach to rail grinding will be implemented as well. So perhaps some really good examples of tribology making a real difference in industry. So I haven't done this alone. I work with quite a number of collaborators, and obviously one really nice part of being an academic is those collaborators can be all over the world. So I've built up a huge network of friends and colleagues around the world. I'd like to thank them very much for their collaborations and the support they've given me. Over the years, I've been an academic, so they've helped me to get where I am today, which is great, hopefully making a big difference to the railway industry. And of course, there's a whole load of other people I couldn't have done this without. Obviously, my colleagues and my students and those researchers that have worked for me, you can see some of them here. Apologies to anyone who's not appeared in a photo, but there are quite a lot of you now. My collaborators, my funders, technicians that help us do what we do in the lab, and of course Vicky, my project manager, who helps to keep my stress levels under control very effectively. So thank you very much to you all, and that's me done.
Great, thank you very much to Roger for this very interesting lecture. This is exactly, it's really another great example of how impactful tribology research can be, and that covering a wide range of applications, ranging from the WheelRail interface to the skin tribology as well. So now we are in the session where we can take questions and have Roger live here to address any questions. So I'll start with the question. I'll read the question, then ask Roger to answer. So, how difficult would it be to modify the Lucchini full-scale test rig to include water jets with the aim of trying to make the test environment more realistic?
Yeah, that would be very simple to do. We don't actually have access to the Lucchini rig anymore, but we've done some more recent testing with the team at the University of Huddersfield on their Harold rig, where we've applied water and various other contaminants. So yeah, that's very straightforward to do.
Thank you, Roger. The next question is, does the material introduced with laser cladding introduce other rail defects, or maybe shift predominant wear towards other defects?
This is a really interesting question, and I think we'll probably find out more about that as we move into doing some field tests to see how the clad layer responds under realistic wheel loading and in the open environment. One thing I should probably note is that we're thinking that the current damage models that are used for predicting what will happen to rail materials aren't now all that appropriate for the kind of materials we're cladding, as they're so hard, and because they don't plastically deform. A lot of the models rely on that kind of deformation process to allow the damage prediction. So it may be that we need to introduce some new approaches to predicting what will happen to these harder materials.
Okay, thank you, Roger. The next question is how can the performance of a lubricant which has been applied on a rail be evaluated to determine a more accurate frequency for lubricant replenishment? Increased frequency could be wasteful on use of lubricant.
Yes, another interesting question, and it's quite right to think about that. When you look at the wayside application of particularly grease, there's a lot of material wastage as the wheels are passing through the grease distribution units. There's a lot of grease splashed around, and there's a lot that isn't picked up and carried down by the wheel. I would say to make the use of a product more efficient, it's probably better to go to an onboard system where you could direct the product to exactly where it's needed in the right amount. That may be some way off for all trains, but so in the meantime, just considering the wayside application, you do have to be a little bit careful in terms of reducing how much is applied, because if you run for a while with no grease present and you start to initiate some damage and cracking on the rail surface, if you then reapply grease, you can quite quickly get some accelerated damage as the grease essentially is trapped in the cracks, and you get sort of crack pressurization, and sometimes you can get quite big chunks of material breaking away. We've looked at that in a lab environment, and yeah, the damage can be quite severe if you have a situation where you've got lubricant there and then lubricant not there, and you keep cycling between them. So you have to take care in changing how much you're applying.
If I can just follow that up with another question on lubricants, Roger. In regards to railway lubricants, is there a standard specification of grease which is ideal?
Yeah, so for example, if you wanted to supply grease to an infrastructure owner, say for example Network Rail, they would have a specification that your grease would have to meet. It wouldn't just be in terms of the constituent of the grease, although that would be part of it. There are a number of performance indicators as well that are required, including tests to assess friction level and retentivity, so how long the grease remains active in the contact, as well as all the other kind of health and safety aspects that they need to consider. So there will be documents available that tell you exactly what a grease needs to do before it's approved for use on a network.
Thank you, Roger. The next question is, there are industry factions that claim that sporadically spraying railway wheels in depots with citric acid is a good thing in order to improve low adhesion performance. What are your views in terms of the effectiveness of this method?
Well, you'll be pleased to know that we are... Oh. Sorry, I interrupted you, Ardian. Yeah, you'll be pleased to know that we're actually running some tests on that right now on our twin disc machine for Network Rail in Scotland, where it is used. So we're looking at how the citric acid impacts the leaf layers. We've also got some swabs taken directly from wheels of trains that have had the citric acid applied. So we're going to be analysing what impact it makes directly on the wheels as well. So I can't tell you right now, but maybe in a month or so we will have an answer on what it's actually doing when it's sprayed on.
Okay, there's a huge number of questions here. I'll select a few, or I'm trying to group them. So the next one is the cryogenic cleaning always fitted behind the train, in which case the train is cleaning for the next train?
Another interesting question. Obviously on the road to rail vehicle video, you saw it fitted on the back. I mean, yes, in that case, obviously the road to rail vehicle cleaning system is cleaning for the next train and ones that come beyond that. With the solutions we're looking at to go on board other trains, we're kind of having to put the system where it will go. For example, on the passenger train trials we'll be running shortly the nozzle will be fixed onto the brackets that's normally used for the sanding device, for example. So in a lot of cases at the moment, we're restricted to where it can go, but it could quite easily go on the front if we were able to design that into the system we were working on. So there's no reason why it needs to go on the back. That's what I'm saying.
Mm-hmm. And there's a question about the noise level of the cryogenic rail cleaning.
Yeah, the noise levels are within acceptable levels. Obviously, we've had to make checks on that since we've been using it in the field, and obviously there are operators within the vehicle and nearby on the track as well. So yeah, I couldn't tell you off the top of my head exactly what the noise levels are, but it's not a problem.
Okay, but considering we're running out of time, I'll have just one final question, and we'll aim to answer the others after offline. So with the introduction of harder rails, has there been any assessment on the impact this might have on wheel wear damage?
Okay, thank you, Andy, for your question. We've done quite a lot of work recently off the back of introducing or looking to introduce the laser clad layers to try and understand the wear of the wheel. You'll be pleased to know that within the kind of typical operating regime of particularly the railhead wheel tread contact, that changing the hardness of the rail doesn't actually have any impact on the wear of the wheel material at all. I haven't got time to go into the full details of that. It's obviously down to the particular mechanism of ratcheting type wear that's occurring there. But what I can say is the wear of the wheel in that situation is completely dictated by the properties of the wheel material. It does change as you get into more severe contacts where you might have higher temperatures forming, but hopefully they won't be very likely anyway.
Great. Thank you very much, Roger. I think we'll leave it there with the question and answer. Thank you very much for your questions, and we'll attempt to we'll forward this to Roger, and we'll attempt to answer them offline. So next, I invite Professor Ian Sherrington to give the vote of thanks to Roger, please. Ian.
Good afternoon, ladies and gentlemen. On behalf of the Tribology Group Committee, it's my pleasure this afternoon to propose a formal vote of thanks to Professor Lewis Donald Julius Groen. Roger's work is well known to members of the Tribology community, and today there's been an opportunity for us to become more closely acquainted with the ways in which Roger and other members of the Leonardo Centre for Tribology at the University of Sheffield have investigated this interface. The contact between train wheels and rails involves complex interactions and many fundamental tribological mechanisms. Today, experimental investigations and modelling tools have been shown to be critical in developing and advancing our understanding of concepts related to adhesion, rolling fatigue, and the effect of rail grinding, sometimes with critical implications for the efficiency of operation of the rail network and for the safety of travellers. And it's clear that Roger and his team are developing solutions to practical operating problems such as low friction due to leaf deposits through this novel railhead cleaning system. Professor Lewis's work is highly regarded, and it's been conveyed to us today with an enthusiasm for the subject and a depth of knowledge that reminds us that here in the UK, there are many people involved in applying the science of tribology who actually are amongst the elite on an international stage. This afternoon, it's been an immense pleasure to listen to one of the great British proponents of tribology. And on behalf of everyone listening, it's my honour to thank Professor Roger Lewis for his insightful presentation. Thank you, Roger.
Thank you, Ian.
Thank
you, Roger, again on my name. This brings us to the end of this year's DJG lecture. Thank you all for your participation with questions. There were numerous. Thank you very much. Have a nice day and goodbye.